I'm David Ross. I've spent all of my time at the VA since October of 1983. When did you come to VA? 84?
My second time around was 87.
87. But
My first time around was 80, which they gave me years credit for.
Ah, well, that's good.
I take it back.
So we have a rehab R&D center, a VA rehab R&D center that's been funded since, I guess, 1981 or 2, somewhere around then. And I came in when they had enough money to hire me in 83. And at first, we worked with a widespread number of disabilities until they kept telling us we needed to focus our efforts on something that made us stand out. So we started focusing more on vision loss and aging, and now cognition. And so, my research over the past 20 years has mainly been focused on issues dealing with vision loss. And that's sort of broken down into 2 categories. There's something called low vision, which means you can still see, and you probably don't use a cane, but you probably also cannot read signs. Like if you had low vision, you wouldn't be able to read what I have up here on the board unless you came up really close to see it. But most of my work has been with people who are classified as blind. That doesn't mean they're totally blind. They have some residual vision that can be useful, but most of them use a cane, and they get around using various cane techniques, and some of them also have dogs. Yeah.
I'm going to put you on presentation.
Oh, well, I can put it up here. You want me to stop talking and start presenting? Is that the idea?
I just was going to put you in presentation mode so people could see the slide, maybe even if they had low vision.
Yeah, okay.
How's that?
All right, it makes it a little, I just
stole your time.
All right. So, some of the projects we get involved in are very long-term. I've been involved in indoor and outdoor wayfinding projects for a long time, trying to come up with a technology that's going to function and not be something that needs to be necessarily cost an arm and a leg to the building owners, because they already have these things called, tactile signs that you had to put over every door. And those already cost you about $35 a piece to have them installed. So we've looked at some other alternatives, including how to include something in those tactile signs that makes it possible to know where they are with your smartphone. But at the same time, we're also looking at low vision, and we started this project back in 1994 and 5, trying to figure out what to do with people who are getting older and whose vision, it may be macular degeneration, but there are also a number of other kinds of diseases that make it more difficult for your eyes to adjust to differing light levels. For instance, going from this light level to outdoors in bright sunshine, say in June, where there's no clouds, you're going from about 75 lux to somewhere around 15,000. That's a huge adaptability range. And most people can see, down to somewhere around 20 to 15 lux before it gets so dim that you can't function. Of course, if you go in a movie theater, it's really low, and your eyes take forever to adapt. But the idea is, for some people, it takes a minute, 2 minutes, sometimes 3 minutes or more when they come from bright sunlight into this kind of lighting to be able to see well enough to start moving around without tripping on something. And that's a real issue. So I started addressing this back in 1984 with a VA merit proposal, and then we followed up later in 2002 with a company called Ashwin Eustace that has some technology we thought might work better than what we developed in the VA. So I already talked about the problem somewhat, but just review this. People who have age-related macular degeneration and other age-related diseases, and even non-age-related diseases, have this slow or impaired light adaptation response time of a minute or more. So stepping in bright sunlight, it's painful to them to go out. However, when you go out in bright sunlight, you can shield your eyes. And so you can still kind of function. If you look down at the ground and shield your eyes, you can kind of function. But when you go indoors, it's a totally different problem. because there's no way to unshield your eyes or to make the indoors bright enough that you can function until your eyes have adapted. So this is the real issue. Walking indoors and not knowing the environment particularly and not knowing what you might trip over. And if you're aging, tripping is a big deal because you don't want to fall, break a hip or something, and then all kinds of other issues start getting piled on top of that. So this is a problem we wanted to address. And we wanted to address it back in the 90s, where we couldn't find technology really suitable. But I'll get to that in a second. So there are a couple causes. Your pupil response changes as you get older. And this is for everybody. Whether or not you have an eye disease, your pupil response will change. Your pupils will not open as wide as they do when you're young, and they won't contract quite as far as they do when you're young. And anyone who's in their 40s and even 50s realizes this already. You're already getting more sensitive to light. And if you're driving at night, you find out the car headlights coming towards you are a real annoyance. Also, if you have retinal degeneration of any form, macular degeneration or others, the retinal cells are also part of the adaptive process. Those retinal cells, in addition to the fact that your pupil gets smaller and less light into your eye, have to adapt to still much larger light levels. And so what they do is they have to chemically change their response to light so that it's not quite as drastic with bright light as you go out in the sunlight. And then it has to be more responsive as you come indoors. And so your eye sensitivity actually manages to change itself through an adaptive process that goes on with the retinal cells and the neural cells that are around them, the ganglion cells and all those, all respond to light in a way that compensates for these things. With a retinal disease, that stops happening quite as well. And so that's the other part of the problem. Also, if you have what's called a scotoma, which is the part of your retina that stops functioning, which is what happens in macular degeneration. There's things called relative scotomas where the nerve cells haven't died yet, but they only respond to brighter light levels. So you can go outdoors and you can see better. You go indoors and you can't see as well. Well, it's more difficult to address this problem coming indoors because you need something called light amplification. But we can address the first two with what we finally developed as dark adapting glasses. So the idea is to combine various light levels by changing how much light actually gets to your eyes through the glasses. And there are products like transition lenses, but the problem is they take a minute or more to change, and they don't really get as dark as someone with this kind of a problem would like to have them get. And they also only work in ultraviolet situations outdoors. So if you're in your car where the windshield is blocking ultraviolet light, they don't function. So you might notice if you're wearing transition lenses that they don't do much if you're driving down the street in the car and the sun suddenly hits you in the windshield. They don't get any darker. Okay, so our specific aims. First, we want to develop glasses that darken and lighten quickly. And here we're talking about a couple seconds. And the idea is that, the hypothesis is, if a prototype reduces the extent to which your eyes have to adapt by these adapting for you, then the process of going outdoors and indoors isn't as drastic to your eyes, and they don't have to adapt as much. And so the adaptation time would be lower. Okay? And the second part is, we want to develop glasses that darken and lighten in a manner that's customized to your eyes. We haven't really gotten to that part other than trying to put additional filters on top of this. But the hypothesis is that if we know your index of light sensitivity, we can adjust the glasses to darken to the extent that you need them for your particular eye disease. And that's still in process. These glasses are just sort of one size fits all, and we sort of adjusted it to those who are sort of in the mid-range. So technology gaps where transitions don't function well enough, they don't function in a car, swapping among a number of sunglasses to adjust to this wide a range of light levels from 75 lux to 12,000. That's like a huge range, is really cumbersome at best. People are given, by the VA at clinic, like 3 or 4 different pairs of glasses depending upon how light or dark it is. Well, then you got to first of all, you have to carry them all around, then you have to switch from one to the other. And if you're outdoors, you know, if you're walking along, you go from sunlight to shade, you know, to walking beside a building where there's not much sun getting to you. And it's just difficult to switch back and forth and back and forth and back and forth all the time. Okay, also there's a data gap predicting, you know, what light, dark range is best to accommodate persons with this problem. And what can we measure about the person that would tell us what's the best range to give them. And the data gap predicting how best to customize glasses for persons for whom the light-dark range that we are able to get with these is not sufficient. Okay, so we started out in the VA with something called liquid crystals. Liquid crystal TVs have been around now for a few years. Basically what happens with a liquid crystal is you have this crystal structure that's a liquid, and you apply a voltage to it, and it moves these long molecules from one direction, one orientation to another orientation. In that process, it changes the polarization of light that goes through this sort of lens or this device. You put a polarizing filter along with it, and when this is polarized and this is polarized at 90 degrees, you let very little light get through. And when you then let this go slowly back the other way, you're letting more and more light get through until a maximum amount of light gets through. The only problem is the best possible filter that you can use is only about 45% efficient. So that even though this might let all the light go through, this filter is cutting back some. So the best you can do is start at 45% transmission of light down to, you know, somewhere around 2 or 1%. But when you go indoors, that's not enough. You need more light. So that's an issue. Also, it's encased in glass. And if you've ever worn glass lenses as opposed to plastic lenses, you know they're heavier. And this is put now on top of your own lens, which makes it even heavier on your nose. And they're energy hungry. They need energy all the time to drive them. A liquid crystal does. And so we then started looking for another solution. But here's the solution we had for liquid crystals in the VA proposal. This is our model, Ben Lonsky, by the way. He used to work for us. He is a double E from Georgia Tech. And on these particular glasses, we used a hybrid to try to get the best range possible. So in this, with the filter flipped up, you have liquid crystals, and you have what's called a guest host molecule attached to these. These molecules absorb light, so as it turns, they absorb more and more light, or not. And so with that, you get a range of about 68% to 37%, which would be like an indoor range if you're walking from, you know, this kind of lighting in a building where you have windows and you have bright sunlight coming in. You can adapt to the changes in indoor light. And then when you flip these down, you have a different range because now you have this polarizing filter, and it gives you a range somewhere around 23% to 2%. And so this would be outdoors. And believe me, 2% is really dark. If you ever had anything that's only letting 2% of the light in, it's pretty dark. And so it meets the needs of everyone we could find. However, no one wanted to wear these. Because first of all, they have a bridge that sits on top of your existing glasses, which so it adds to the weight of your own glasses, and it's putting it all on your nose. So we started looking for something a little bit better that would function in a way that didn't have these issues. And what we came up with at a conference where we were presenting this was a company came up to us and said, well, you know, we do these tinted window plastic coating things, and you apply a voltage to it and it changes the tint, and that sort of works. And we also have a contract with DOD to put these on, you know, jet pilot windshields, et cetera, jet airplane windshields. Sorry, that's okay. So I said, well, was that going to work? And they said they could give us a range of about 87% down to 23%, which is a middle range that works for, actually, as we tested these, a majority of the folks who need this problem addressed, except for the extreme ones, and I'll get to that later. They're very lightweight because it's just a very thin plastic coating. We wanted to put them on lenses, but they said, well, we can't do the sort of 2D thing where we can do a 1D where we can bend it across this way. So this is actually something you still would have to wear. And there's now an insert that you can put in here that has lenses on it that I didn't bring, so you could have that. And it requires very little power. The only time you need power is when you want to change it from one darkness to another. And you move it both either positive or negative, and it will change how much it absorbs or doesn't absorb light. Our initial problems were, though, that when you took it outdoors in the sunlight, ultraviolet light and that plastic didn't work well together. It started degrading, and these things stopped working after 2 to 3 months. So that was an issue. And then there was visual imperfections in these things. When you coat a window with something that you want to, to let less light in or adjust the light, you don't care, that there's little imperfections in it. But when you're looking through this and your vision is dependent upon it, you need to have it, perfectly the same all the way, the same darkness. So that's another issue we had to resolve over time. And we finally, in 2009, finally came up with these lenses, which look, you see maybe a little bit in here, but we got even better than this to show the kind of lenses we were going to be able to get. You can see little spots in this and little spots in that, but this is still in 2009, and we were still working on it, but we were getting better, a whole lot better than, I should have shown you a picture of the ones that were really bad. But in any case, oh, this is 2002. Okay, these were some of the original ones then. They had the spots in them. And we were looking at what voltage to apply to them to get them to change light and dark. And we had this whole lab set up, something that's actually not in existence anymore. This is Ben again. And we had to set up, this huge thing is called a photometer. It's measuring very carefully how much light's coming through. There's a projector on this side. There's a screen there to even out the light coming to the lenses. And we have sensors on these glasses that are telling us how much light is getting through. And we're looking at how to adjust the voltage to get the light coming through to adjust to the levels that we want it to be adjusted to, so that it ends up as much the same coming to your eyes as possible. And here we have, I don't know if you can see it, but there's a circuit drawn out back there that Ben was working on to control all of this. So we did, we did from basic research, to human subjects. And this guy named Jim Marston, who joined us in the mid-2000s, and this is one of the first ones that actually was clear enough that you could walk around and see well. Of course, you can see there's wires, and it goes to a battery pack and some other stuff back there. But this is like the first version that we could actually have people wear, and started testing. And then we came up with a version where we put the batteries and the circuitry into this piece that sits behind your ear. And then we came up with this version where, well, this is a battery essentially taped to the side, and, well, a circuit taped to the side and battery on this side and a little switch there. And this is me, of course, and wires are sort of taped around it. And what we did here was we took a picture of me indoors and a picture of me outdoors, and then split it so you can see light and dark, how it changed. And this is the pair we have now, which is this. And in this pair, this piece in the middle is where the sensor is. The lens actually comes all the way across both sides. So it's covering the sensor. So the sensor is actually measuring how much light is coming through to your eyes. And it's set up so that as light coming to your eyes gets more and more intense, it gets darker and darker and darker in response. To demonstrate this, since we're not outdoors, I brought a rather bright light. And you should be able to see that it gets dark. I should put this against something. Let's see if I can. Screen is light. Put this here, it should get dark. Can you see it's darker now? I don't know how well you can see that. If I put it over. Do you want to try it? Or I put it on. Oh yeah. I'm just wondering if you can see my eyes. You can probably see my eyes now. Put this here. should get dark. Well, I can't see how well I'm aiming the light. Did it get darker? Well, it got darker, but I don't know how well you can tell. Yeah. Well, anyway, maybe you can come up afterwards and test them out. Get a sense for how it works. So now we have the glasses we wanted. Now we wanted to do the testing to see how well they're going to work. So we set up a lab. We call this our bright lab. Here we have it in the dim mode, which is about 75 lux. And here we have it in the bright mode, which is around 8,000. And we have a chart for reading. What we did was we had the subjects come in and under normal light, figure out how far down this chart they could read. Now this is there's two kind of charts. There's a acuity chart and there's a contrast sensitivity chart. The acuity chart is sitting over here right now. This is the contrast sensitivity. And you can tell as you get further down, the contrast gets less and less and less until you probably can't see the last line at all. Excuse me. So in normal lighting conditions, we find out where on this chart they can read. So say they could read down to this line, NOD, and then we bring them into this lab, and the chart, we have a different chart with different letters on it with the same contrast of this line, and we ask them, we point to this line and we switch it from dim to bright before we reveal the chart, and then we point to the line and say read, and we time how long it takes their eyes to adapt to the brighter light in that process, and then we do the reverse with a different chart at the same line to see how long it takes their eyes to adjust to the dimmer light. And then we compared this to the sunglasses they were given by the VA eye clinic to use. So they used both our glasses and this other set as a comparison. So, demographics. Total number of subjects we had at this point was 55. 25 had come into the lab only for these tests, and 30 more had come into the lab for a test and then gone out to the community and were using these glasses for 3 weeks and writing out a diary about what they liked and didn't like about them and where they worked and where they didn't work. I've got a slight cold, so my voice is starting to get hoarse. Recruited them all from the VA eye clinic. Unfortunately, in the VA, you don't find very many females, so we only had 2 females and 53 males. Age range from 58 to 95, mean age 72, standard deviation 9.2. Race 36 Caucasian, 18 black, and 1 Pacific Islander from Hawaii. And we have a range of eye diseases from macular degeneration to glaucoma, pigment retinal dystrophy, and diabetic retinopathy, et cetera, et cetera, et cetera. I don't know if that means anything to you, but and duration of their problems, 10 years or greater, we had 29, 7 to 9 years, 8 subjects, 4 to 6, 14, 1 to 3, 4, and less than 1 year, none. We sort of screened out the ones that hadn't adapted yet. Now we looked at what's called photosensitivity, which is the test that you can give them to see how sensitive their eyes are to changing light levels. And the range of these subjects was from 0 to 38. Zero means you have no sensitivity to light. It means you can't see. And so for some of these subjects, in one eye, that was the case. 38 means you're very sensitive, overly sensitive to light, so that you have a real issue. And in the mid-range, it's varying degrees. So our mean was about 20 in terms of sensitivity, and the standard deviation was 11, almost 12. But we found a lot of cases where there was a big difference between their eyes. You know, the difference between one eye and another as a mean was 20, which is huge. And the standard deviation was 11, almost 12. So we have one eye and another eye actually acting very differently. And so then we have to say, well, how do we adjust these? Because these actually do the same thing for both eyes. Do we really need to compensate for both eyes? And what we decided to do was go with the eye that's the most sensitive and look at that. But we actually had 15 cases where, one eye had 0, no light sensitivity. So basically we were looking at the other eye. And sensitivity is greater than 20 across eyes. And then we had people with scores greater than 30. Now these people with greater than 30 are really, really sensitive. So what they were prescribed by the eye clinic was actually glasses that got darker than the ones we were able to make. So we were interested in what was going to happen with this group.
So,
Yeah.
last slide, the between eyes and the overall, the mean and standard deviation are exactly the same down to the 100. Is that?
That's interesting. I need to look and see did I copy that right? This is the actual.
I mean, I believe you that
This is the actual data. Maybe I didn't. Maybe I copied that wrong when I looked at it. Well, I guess it's not in this chart. In any case, this is a comparison again with their own sunglasses. So we looked at were they able to respond more quickly with ours versus theirs. And so what you're seeing is a difference between the two. So for the transition to bright, we came out about the same as theirs. For the transition to the dim, we came out 27 seconds better than theirs when we're looking at acuity. From the transition to bright in terms of contrast, we came out just 4 seconds better, which is not a significant difference. And the transition to indoors again, we came out almost 26 seconds better than theirs as a mean. So that clearly going indoors, we're doing better. And when you're talking about 25 to 27 seconds, think about you walk into a building and you got to stand there. How long is that 25 seconds going to feel to you as you're standing there while people are pushing in behind you saying, keep going? So that's actually a very significant difference. It's the brightness that's the problem. And again, what they tended to do was they used their hand to shield the eyes, and they could function with the bright. So it's really the dark cases that we're looking at as where we really have an advantage. And that's the mean. The maximum for the bright was really good for some people. 42 seconds, they could see faster than what they could say with their own. 154 seconds going indoors. We're talking about 2.5 minutes. We had the advantage in going indoors for that guy. Now this is just one person, but this is a maximum we hit. And you see the same thing, on the, on the other. So for some people, yeah.
So if you were going from outdoors indoors and you had a brightness sensitivity, you would probably be wearing sunglasses to start with.
Yeah.
Or if you had transition lenses, which take several minutes to
It would take them off.
transition down, then the transition from outdoors to indoors wouldn't be nearly as important as the transition from indoors to outdoors, where your lenses are in transition, for example, are not dark. So
Well, for transition lenses, that's true. But no one is prescribed transition lenses. They're prescribed regular dark glasses that are sufficient for them, to function outdoors. And so what was happening here is they were when we had the bright lights on, they had their dark glasses on, and basically when we switched them back to dim, they took the dark glasses off so that they could see, because otherwise they wouldn't be able to see at all. And it was still doing better for them because of the fact that these were dark and then got light right away, and their eyes then didn't have them as much to adjust to, if that makes sense.
well, I understand that these are better in terms of being faster in the transition, but it seems to me that the more important transition would be indoors to outdoors than outdoors to indoors.
Well, when you go outdoors, you have other strategies you can use. You can shield yourself from bright things and glare. Yeah, and you can look at the ground. When you go indoors, there's no strategy you can use other than just wait for your eyes to adjust. That make sense?
Come on.
Okay. So, and this shows the standard deviations in each case. So here, the number that actually did better in all cases here was 18 out of the 53. Going indoors, it was 46 out of 53, did significantly better. Going out into the bright, 29 did significantly better, and then 46 going indoors. That's 46 out of 53 again. So there is a group of these people that this works best for, in both cases. And then there was a number ahead where basically there was no difference, no significant difference. And then, okay, that's better. This is significantly better. So 9, 36, 17, and 39. Significantly worse was 5, 1, 7, and 1. Yeah.
Did you also do, I mean, you did it with kind of the glasses. Did you test them as well, just in the same methodology without the glasses to see how it compared?
We did it, well, the comparison was with what they already were using.
Oh, yeah, that would make sense.
That's the comparison. So this includes that comparison. In other words, the seconds, when I say 1 second better here, it's 1 second better than what they were getting using their own sunglasses. Okay, this isn't the actual length of time. This is the difference. Okay?
So you're measuring how much better than their current.
Exactly. Right, we had to compare it with something. And we couldn't compare it with them using nothing because they couldn't see at all, most of them. So we had to compare with what their existing sunwear was to see how much better we are getting than what they've been prescribed by the eye clinic. That make sense? Any other questions on this? Okay, so in summary, so for a transition from 75 to 8,000 lux, the mean time was not improved for anybody in a significant fashion. However, for 15 of the 55, they did perform significantly better with our glasses than theirs. And for
Give us sort of what 75, 50,000 lux is in terms of something that we can wrap our heads
well, this room is probably somewhere around 75 right now. 8,000 is the brightest we could get in a room. If you go outdoors on a June day in bright sunlight, no clouds, and white concrete around you, you're somewhere around 12,000. And about the brightest day you can imagine in Georgia. And so we got up to about 8,000, which is 8,000 out of the 12,000, which is, most of the way there, but not quite. Lux is a logarithmic scale, by the way. So 8,000 out of 12 isn't well, it's a 4,000 lux difference, but that's a log difference versus a linear difference. So anyway, 8,000 is pretty bright. If I could turn this room into our bright room, you'd have to, shield your eyes. And the photograph I have of the bright room doesn't do it justice because the camera adjusts to the light level and just shows, oh, there's bright lights in there. Yeah.
And how much lux would be like a perceived doubling in brightness? So, for example, from like 50 lux to 100, would that be like double brightness and 100 to 200 because it's on a logarithmic scale, so the perception
Yeah.
of it would be different necessarily than the
Right.
actual light amount.
Yeah, so our perception is basically logarithmic. That's why they use this log scale. So if you're an engineer, you know how, 1, 2, it gets tighter together as you get, it looks like it used to be like a slide rule, but
So to see the improvement that you're seeing, this requires the person to have been wearing the glasses in the 8,000 lux
yes,
before walking into the 70.
exactly,
So basically, it kind of tempers that 8,000 lux so that
exactly.
transition.
So at 8,000, these are as dark as they can get, and so it's bringing the light level down to something that's from which a change to a lower light level isn't so drastic. And so,
So presumably, if you knew that you're about to go indoors, you could probably put these glasses on maybe a couple minutes in advance.
yeah, well, the idea is that you would wear these all the time, outdoors and indoors. That's the idea. A lot of people, when they went home to the community, we gave them to them, and they just wear them all the time outdoors. Because as you're even walking around outdoors, they say, well, it's better because I can walk from shadow to bright sunlight, and it doesn't affect me. I can see clearly, which I'll get to in a minute.
So if this is equivalent of 75 lux, and you were an older adult that had vision problems, then probably 75 lux coming down to that is going to be too little to sort of see the same sign that you were talking about earlier.
What-
This isn't enough light for somebody that has difficulty with acuity.
75 lux is fine as long as you're adapted to it. For people who have, I had in the initial thing a problem called relative scotomas, where when you get down to this kind of light level, whole parts of your eye just stop working. This doesn't solve that.
If you have age-related vision loss, not
Yeah.
from some visual condition.
Right.
75 lux is pretty low for you to be able to read signage in a building or to read. So
It's-
if you're coming down to 75 lux, and I'm not sure where, how you decided what 75 lux was, but.
Well, it's
or
basically
75.
normal hallway lighting in the VA.
Exactly, which isn't enough to actually read signs if you have, vision loss.
Well, it depends on what your vision loss is. These people, we conducted the initial test of their vision at 75 lux as a standard, and so they were able to read that far down the chart. So we're just comparing what they were able to do at 75 lux with what these glasses could help them do. That's all. And if someone had problems at 75 lux and couldn't read any further down the chart, then that's as far as they got, and that's where our comparison was. Yeah, there's people who do have more problems.
And so, we're talking about a lab study, and
Right.
I'm just wondering when this gets to a real-world application, whether 75 lux is coming down to 75 lux is actually going to be sufficient.
Well, people
For
who,
people, particularly older adults, to be
Yeah.
able to see and function.
well, it certainly, yeah, it's an issue, but the glasses don't bring you down to 75 lux. The glasses get as clear as they get at somewhere around 150.
I see. Okay.
So it's not the glasses that are taking you down there. We just did that as a lab. For the take-home stuff, people had their homes lit at whatever brightness they felt comfortable with, and that's what they were being evaluated in. That makes sense. Am I going over time?
Yes.
Yeah. Let me get to the,
Okay. You can ask questions along the way.
yeah. Where was I? So,
Position 8,000 to 75.
yeah, so basically, in the bright condition, we had a number who were, if you were in this foveal sensitivity range, you did okay. You did better. But if you were outside of that range, either lower or higher, then this is a problem for you. So we were sort of, as I said, there's a question about what sort of range we can address with these glasses, and this is sort of the range we got to that worked. In the transition going from bright to dim, we were better off with the improvement of about 26 seconds for 38 out of 55 people. And these are also people in the same sort of sensitivity range from 18 to 28. As you get to 30 and above, it's really sensitive. And something else, you need something else to make things even darker indoors. We have people saying, these do not even go dark enough for me inside. So that's pretty sensitive. We noticed that for the bright transition, they could shield their eyes. Again, I mentioned that. We need to be able to customize glasses, however, for those who are outside of this range of 18 to 28. I know that number doesn't mean anything to you, but basically below 18, you have very low light sensitivity. You need to see more indoors. And above 28, you're getting very sensitive, and you need these glasses to go darker. Yeah.
So were those the people who found that their existing glasses were better than?
Yeah.
Okay.
The ones who were above 8 or 28 were the ones who said, well, my glasses are better because they got darker. Yeah.
So what percentage of your population did that 18 to 28 cover? Because if your mean was 20, standard deviation was 11, then yeah, I'm guessing that it's around, what, 30 or 40% of the population?
It was, I need to look, let's see, what was it?
Or maybe not.
We had 55 people, and for the going into the dim light, it was 46 it was working for. So I'm guessing somewhere around 40 out of 55 sort of were fit in that category. I have to look at the data again to see exactly what the fovea range for those particular people was. I want to get to the next slide though, because this is the community use out in the community. This is my last. So we gave them these glasses to them to take home for 3 weeks to try in their own communities, walking around and driving. A lot of them drove. And basically, what they liked was they liked the seamless transitions, basically going into dim light. This is the thing they most liked.
Sorry.
That's okay. Going into dimmer light as they walked into their house or they walked into a store or something. They really liked the fact that they could walk in and they didn't have to stand and stop and wait. They could keep on moving. They liked the fact that they could see better with these than their own sunglasses. They liked the fact that, no temporary blindness as they came indoors. A number of them were driving, and they said it was much easier to drive, especially when they're driving in sunlight conditions, because these had these glasses that were adjusting and helping their eyes, see better on the road, and gave them improved clarity, resolution, and more definition of objects. What they didn't like, they said, the people who had more sensitive eyes didn't like the fact it didn't darken enough. They didn't like the sides of the frames. Now, we tried to round these to give you a better, side view than typical glasses, but when you add in lenses in there, it pushes you a little further away, and you have this side frame that got in the way of some people. So we had to sort of look at that and see how we can adjust that so that doesn't become a problem. Frames are too big and heavy. Well, you can see how these aren't terribly heavy, but when you put glasses in there on top of it, it gets a little bit more heavy. And they thought they looked more like safety glasses, and some people were kind of style conscious. And then they were saying, we got negative comments from our friends. They said, you look strange, like some sort of alien wearing these things. So, we can look at the style issues. The company is actually going back for another SBAR for getting these into manufacture, and in the process, they're going to look at a number of issues. They're also, the battery is built into the frame, and the circuits are built into the frame, and there's a, push button to turn them on and turn them off, and there's a thing to charge them with. And some of these are also some issues that they mentioned, but they didn't have anything to do with the functioning of the glasses themselves. And so these are other things to take into consideration as we look at making this into a product. Okay, now I'm done. Any other questions? If you can stay longer, that's fine with me. Yeah.
So, have you thought about taking this in a different direction and perhaps to account for the second question or the second aim that you haven't addressed, that is sort of the customization or individualization?
Yeah, the company is looking at that and how to put a darker film in. The problem is, let me go back to the slide where it gives you the range.
My question really
Probably is the range.
isn't about the current technology, but to overcome the shortcomings of the current technology in terms of customization and in terms of
Right.
getting dark enough. Have you thought about perhaps just giving somebody really dark glasses and using binocular cameras to provide information directly to them underneath the glasses?
So you're just talking about like a virtual reality glasses, and then you see what's.
Whatever it is.
Yeah, well, that's a more expensive technology, but it's certainly possible. There's people making these. I mean, virtual reality glasses are coming out now. There's like 4 different companies making them. And there's, what is it? There's one company, I forgot who they are, but they are making these. The issue with those is, can you get a display that's bright enough for some of these people? I don't know. It depends on what kind of display you can get. You know, in terms of what we're looking at, you know, it's 87 to 23 range is what these things can do. If you put a filter on top of that, you can cut back the 23 down, but you're also cutting the 87 down. So you're sort of compromising between higher light levels indoors and lower light levels outdoors. So if you cut the 23 down to say 10, you're cutting this also down to around 50. So you have an issue going outdoors or indoors that you don't have as much light coming in that you might need. So it's a matter of, can we increase that range, and then we can filter it. You see what I'm saying? We have a range of 87 to 23 is how much of a difference we can get. But then if you start putting a filter on top of that, you're lowering both the top and low end. Am I making sense? So that's something that the company is trying to address in terms of, this guy is a chemical engineer. He's trying to look at, well, how can I actually make this range wider, and then it would go darker. Yeah.
So beyond the everyday application of just, walking in a building and adjusting lights and, the perception of light, what other applications do you see for this kind of technology? I can clearly personally see that in construction or in military, where you're constantly out and about and adjusting and need that fast.
Yeah. Well, I mean, I would wear these just to drive in traffic every day with the sunlight we have, because they change very quickly. And I don't have this problem, but still, glare is glare. And when you're driving along a lot of traffic, coming in the morning or going out at night, you have, well, in the mornings it's dark right now, but at night going home the sun's out, and you get, if you're driving in downtown, you get buildings blocking the sun, and suddenly you're hit by the sun when you get to the intersection, and if you're driving out along roads outside of the city, you have trees. So it's always, something I would think it would be a general product. And the nice thing about making it a general product for everybody is that it brings the price down so that the people who really need it, can afford it. Sort of like how we're aiming this. Anything else? Okay, well, thank you.